Okay, welcome back to science. I hope that you enjoyed watching the video from yesterday, especially the video with the guy doing the experiment with the egg. If we were in class, I've always done this one and it's pretty cool to do, but he does a really good job of it as well. So I just wanted to, we're just gonna watch this one more time and then just talk about the concepts before we go on to our new part of today. Okay, so here we're back with Jared and he has this boiled egg. Okay, let's see here. Okay, he's done one over here. Where he gets this inside of the case. Anyway, we'll just watch.
Try and demonstrate that. Let's try it again with a smaller bottle and see what happens. But remember, if you're gonna try this at home, you need a good pair of safety glasses or sunglasses to make sure you're safe. So, here we go. Let's try it with a smaller glass bottle. It's important to use glass because plastic could melt. So, light the match, get my paper burning, drop it in.
Boom!
The egg went right into the bottle.
Okay. All right. Okay. So why is that happening? Okay. There's a lot of different concepts involved which are happening in order to create the egg going into the bottle. So the first thing which we have to think about is going back to our oxidization, right? What is this a form of when there is burning? Okay. What's happening? It's called combustion, right? Because that means that something is burning. So in order for there to be fire, fire needs to have oxygen. If there's no oxygen, then the fire simply won't be able to, exist. And that's also why if you're like making a campfire or whatever, if it's like going out, then the tip is to like get down right to like the base of the like where the logs are and then blow on it, because that helps the fire generate faster. So what he did here is he put the piece of paper into the bottle, right? And then he put the egg over top. Well, I don't know why my video is doing this these days. It's so weird to me. Okay, so he put the egg on top, right? Which created a seal. Now, of course, let's just sort of watch the flame.
Of the bottle. We're going to try and demonstrate that. Let's try it again with a smaller bottle and see what happens. But remember, if you're going to try this at home,
and you guys can try this if you want.
Glasses or sunglasses to make sure.
It's tricky with the right size of bottle, though.
So
that's the key.
Here we go.
It's tricky.
Let's try it with a smaller glass bottle.
Okay.
It's important to use glass because plastic could melt. So, light the match.
Okay, watch.
Get my paper burning. Drop it in.
Watch how long it stays in for. Okay.
The egg.
Okay. So did you see that? Watch how long the paper actually stays lit.
You're safe. So, here we go. Let's try it with a smaller glass bottle.
Okay, watch how long you can see the flame.
Because plastic could melt. So, light the match, get my paper burning, drop it in.
See, it's out already. Okay.
The egg.
Cool. Okay, so there, if you saw that, the fire wasn't going for very long, was it? It was just up for a very short amount of time because basically what happened, we'd be talking about this if we were in class right now, but basically what happened is the oxygen got used up and then it was gone. And then think about the pressure the air pressure inside of the bottle. All of the little oxygen molecules had been sucked up. So there is low amounts of oxygen, so low air pressure inside of the bottle. So what was actually happening, rather than it kind of created a bit of a vacuum in a way, but really what caused the egg to go inside was the air pressure above the egg. It was greater air pressure above the egg than inside of the glass because the oxygen had been used up. There was no particles left. So that's what caused it to pop in there, which is kind of cool. Okay, anyway, there's more of that video if you wanted to watch more of it. But I just wanted to explain that one concept to you because that's kind of the most critical part. But you're going to see that on the science page here, this is the link to the video. Okay, so you can easily go there. Okay, alrighty. So today we are going on to something new, which is called Bernoulli's principle. And we'll be doing this today and also tomorrow, and then on to flight, because Bernoulli's principle is a critical principle to understand with flight, how flight is possible. Okay, so we need to write this on a new page. Okay, so what is Bernoulli's principle? I can describe and demonstrate instances where air movement across a surface results in lift. Okay, which is Bernoulli's principle. All right, so you might need to pause me if you need to, just to write that down. Okay, so we're describing what Bernoulli's principle is, and then we're also going to talk about different situations where that occurs or it can be demonstrated. All right, so here's a little bit of background on this dude Bernoulli. Daniel Bernoulli is his name. He lived in the early 1700s. He was a very famous scientist and mathematician who studied fluid dynamics. And fluid dynamics is actually a whole entire course. If you are someone who wants to be an engineer one day, you could become a fluid an engineer who specializes in fluids. So like oil and gas, there'd be a lot of engineers who have to really specifically know fluids. My sister has a degree in engineering, the one who's now a doctor. I remember that she really enjoyed the fluid and dynamics part of engineering. And now, lo and behold, she is becoming an anesthetist, which is someone who basically puts people to sleep. So it's important to regulate the fluid exchange between the lungs and the heart, I guess, and the drugs are being pumped into the person so their body's able to be okay during an operation. So that's fluid dynamics, which is so cool. And then same thing for like people who are inventing, engineers who are inventing airplanes or rockets or even like bikes or fast cars. It's important to understand fluids, how fluids move. Okay, so we made this huge discovery way back in 1738. Okay, and basically this is his discovery. He discovered, I'm going to show another sort of thing again, but this is basically it. So he observed fluids, which were both liquids and gases. He knew that they had very similar principles. That is the velocity. Velocity is, I wonder if anyone knows, velocity is speed. Okay, so as the velocity increases, that results in the pressure going down. So as it's moving faster, there's less pressure. Okay, now that's really easy to get mixed up, but we're gonna do some demonstrations to further understand this principle. Okay, here it is again. So I do suggest that you write this down. You could write down the last slide if you wanted to, but I have it again in a bit more kind of clear understanding. So this, I think, you don't have to write this in either if you don't want to. So his investigation, he was curious about what happened to water when it flowed through partially blocked pipes. So he had these pipes set up like this. And he might have also, he did many experiments. This has just been one of them. So he has a full normal pipe, same amount of water, same volume of water going in, and then it goes out as well, right? Partially kind of blocked. This is more blocked, less for the water to move through than here. Maybe he also could have stuck gum in there, or I don't know, maybe it's kind of the same thing if you guys ever have like a water fight and you have a hose and then you're like covering over part of the hose so that it goes faster, right? You're blocking it so there's more velocity, more speed behind the fluid. Okay, so what he did is he experimented with different sides of pipes and kept track of the differences and the speed of the pressure of the flowing liquid. So, whoa, this is all of his work here. It's like crazy. You do not need to understand this. This is like university level stuff. But yeah, basically he kept track of the speed. So how fast the water was going here and then what the pressure is. And then same thing here, the speed and the pressure. And the pressure is measured in these things called newtons, N. If you see any N's in here, that's where it is. Yeah. Okay. So he explained how fluids are like water and air flow. Okay, so that's what he wanted to come up with. All right, so dun-da-da, you need to write this down. Make this huge on your piece of paper, okay? We're also gonna draw some stuff around this as well. So it even would be kind of cool to draw this diagram and then we'll label it according to this side. Okay, so high air speed or high water speed, I guess, high fluid speed, but we're talking about air, like our units being the air and aerodynamics. So Okay, so high airspeed equals low air pressure. So the higher the speed, the higher the velocity, the lower the pressure. And then low airspeed, so if it's traveling slowly, it is high air pressure or high fluid pressure. Okay, so I'm just gonna explain this a little tiny bit more, and then we're gonna do a demonstration to show this, which is pretty cool. Okay, so if you think about it, kind of like the leaves that we had the other day, right? Or shown in that video from the other day, okay? If you have a whole ton of leaves here, which are moving slowly, okay? Imagine you have this like your hand, and on your hand you have all of these leaves that are moving slowly, okay? The leaves would represent like an air molecule. And they're just hanging out, they're just chilling. They're not moving very fast. You're gonna feel that, right? Like you're definitely gonna feel that weight, even though it's just leaves, you're gonna feel it on your hands. If anyone's like ever raked before, like cleaned up leaves, you know that when you have a whole like bag of leaves, it's heavy, like really, really heavy. Okay, then imagine you have these leaves that are like fluttering around and they're going fast, okay? They're moving quickly on your hands. Would you even be able to feel them? Probably not, because they're going super, super, super fast. So that kind of helps us understand low speed, low movement of these leaves, low movement of the molecules, it's gonna be heavy, okay? High speed is going to be light. We're not even gonna really notice that it's come by us, okay? So I think that's kind of the easiest way to like a little bit wrap your head around it, okay? Now, here is the next thing, which is gonna show this a bit further. Okay, so Bernoulli, again, discovered that water flowed faster when it went past an obstacle, right? So if you think of like, I don't know, like even like a rapids or something in the river, if there's a whole ton of like rocks or like a narrowing or like a lazy river kind of thing, right? You know, it's gonna zoom by like way faster. And then whenever the water flowed faster, it lost some of its normal pressure. So that means it's like, we can't even detect that the like molecules are even there. They're going so fast, we can't feel them. Okay, so there you go. This is maybe something else that might help you. You might want to draw this down as well. So high air pressure, okay, high pressure, lots of these, like think of like these little red arrows as like the weight, right? It's moving slowly, it's heavy. Zooms by fast, light, low pressure, high speed, and then again over here, okay? Alrighty, so now what we're gonna do is we're gonna do an activity. We're gonna do 2 activities today. The first one is called magnetic paper, okay? I would like you to write this down. So we're gonna do, maybe what you could do is set up your page so that it's like 2 activities, okay? One is called magnetic paper. So maybe on like half, I'd even suggest like 1 full page. You could have had like all that stuff on like fast, air speed, all the Bernoulli principle stuff. And then on your other page, this is so important, this stuff, you could write magnetic paper and then leave the other one blank for what's next. Okay, so, and it'd be good to set it up like this kind of as well. All right, so what happens when you blow between 2 parallel pieces of paper? Okay, like this dude's doing down here. What's gonna happen? So you have to make a prediction. And then why? Okay, why do you think that is happening? And your prediction, or making up a hypothesis, a prediction or a hypothesis should always include something that's like, because I know, well, what do you know? Like what principles have you just learned? So think about this. Where is the air moving fast? Where is it not moving as fast? Okay, so write down a prediction. If you're in class, I make sure everyone did this and you talk with your friends about what you've written. Okay, so now what you need to do, you can pause me before you make sure you have your prediction, okay? Then we're gonna do this. So you have your pieces of paper, okay? Holding them parallel like this, okay? Then what you're gonna do, not too far apart, is you're gonna blow between the pieces of paper. And what is going to happen? What do you think is going to happen? Okay, so let's see here. What do you notice? There, I got it really good that time. Okay, what did you notice? So the paper, it was like magnets. It went together, right? Why? Why did that happen? Why did that happen? What was happening with the speed of the air? Normally we think that if we blow something like, right, it's gonna like blow away from us. Like, it's gonna just like go away, right? So maybe you think that if you blew, the paper would be further apart. That would be a normal prediction to make, kind of. But now we know more about air pressure and air speed. So, okay, hopefully you've written that down, and then it'd be cool for you to like draw in also what happened. Okay, but I'm gonna explain this now with some little debriefing notes. So I suggest that you also write this underneath. Okay, so we'd be taking longer if we were in school to this, but this is basically what happens. Okay, so Bernoulli's principle explains that fast-moving air creates an area of lower pressure than when it is moving slowly. Okay, so still air has high air pressure, which presses the two pieces of paper together. Okay, so, right, so we have our pieces of paper. Where is the air moving quickly? Between. So what do we know about the air pressure between the pieces of paper? High speed equals low air pressure. So then what is actually causing the paper to press? The low air speed, which is just like the normal air outside, it has high air pressure. So it's actually pushing in on the pieces of paper. So cool. Okay, so that is, so that is the first demonstration. Now the second one is going to be for you. So, okay, this is what you have to do. And this is your homework, which I'm going to be posting the next page, which I'll explain to you, onto Seesaw, okay? So what will happen to the bridge when you blow under the bridge? So what you need to do, okay, to make a hypothesis, I'm going to explain the experiment to begin with. So you have to get a piece of paper and then cut the piece of paper in half, okay? So just a normal piece of paper like this, cut it in half, okay? So I have scissors, I'm not sure I'm going to do it. Okay, so cut it in half, okay? Or I guess you could fold it too. It's not going to work for a full piece of paper, that's what I'm suggesting. Probably like this will work as well. Then you need to make this little bridge. Okay, so you can figure this out. I'm not going to tell you how to do this. This will be good for your brains to come up with how you make this little bridge. Okay, so then part of your Seesaw assignment is going to be, you have to make this bridge or else it will be difficult understanding how like the actual concept works. Okay, so what you do, make this, set up like this. Okay, then using a strip of paper to build a bridge that looks like the picture above. Okay, done. Set Bernoulli's bridge on a table. Done. Gently blow under it between the table and the bridge. So you're going to be blowing underneath here. Okay, so you're going to make a hypothesis first. Observe what happens. Try with varying speeds. Okay, so first of all, hypothesis. What do you think is going to happen when you blow underneath of the bridge? Okay, and then why? So I'm just going to show this. Okay, this is what you are going to have in Edmodo today. Okay, so, okay, so hypothesis. So I want you to write this in. Or sorry, not Edmodo, Seesaw. Then here, okay, so procedure, blah, blah, blah. Then observations, okay? You need to draw the bridge, again, under here. Okay, then you need to label where the air is moving quickly and the associated pressure. So I want you to label the where the air is moving quickly and also conversely where the air is moving slowly, and then say the difference in the air pressures. Okay, that should be labeled, and like a picture, like what actually happened when you did this. Then analysis conclusion. So I want you to say what is causing this to happen. What happened? Like why did whatever you observe happen? Okay, using some of the concepts that we learned in this class. So that is it. That is due tomorrow, okay, by, let's see, like 1 o'clock. Yeah, 1 o'clock. And then I'll go over this at like in our second class. So same thing as math. If you do not do your homework, I'm not giving you the marks, because then I go over it and then you just copy what I say. So There's no point. So please do this lab, okay? It's not going to be too much, and you haven't had any like science homework in like over a week since the oxidization thing. So shouldn't be that much to do, and it's kind of fun. Okay, so it's in Seesaw. You'll see it right after you finish this. Okay, if you have questions, then just wait, and then we can talk during social studies as well. Okay, good job.